How's it going? This is Kyle, and I'm going to be doing homework 2, part B of for computational methods, and in which we're going to derive the expression for entropy of a probability distribution. So let's get into it. The example we'll be using is like students in a grade distribution. So we'll say that we have 1,000 students, and there's different grades that you can get, and we'll just put it in tiers from 1 to 10. So there's a few different breakdowns you could have of the class's grade distribution. So just look at it on a line. So there's 1 all the way up until 10. So we could have the groups evenly distributed, like we could have 100 students in each group. And then we could have something else that's like same thing, kind of 1 to 10. And we could have it like split a lot differently. Like we could have like 500 in 2 different groups and nothing in anything else. So a term used is entropy, and that's kind of addressing like the likelihood of the different distributions for a probability distribution. So the formula for that is that entropy is the number of students factorial divided by the product of the number of students in each group of grades. So that's what I called I. We'll start at 1 and you run through all your groups, and we have 10 groups. And then we'll call Ni the number of students per grade. So then it's the product of n factorial from, Ni factorial from I starting at 1 to our max, which in this case we are doing 10. So for example, for the 2 situations I described, our entropy would be like 1,000 factorial over the product of like 100, for the top example, 100 factorial times 100 factorial times 100 factorial, and continued all the way to 10. And then for the bottom one, it would be 1,000 factorial again, but this time over top 500 factorial times 500 factorial. And then it could be any, those are just 2 examples, it could be any number of the breakdown. So we're going to derive this expression to be a little more usable, because these numbers can get extremely large when you're getting into 1,000 factorial. So to do this, we're going to use Stirling's approximation. And Stirling's approximation says that the natural log of a factorial number is approximately the number times the natural log minus n. So natural log of factorial is equal to n times the natural log of n minus n. So now if we take our entropy equation, we just take the natural log of that. So that won't actually change the, it'll just kind of reorient the values, keep the relation the same. Then we can really use this approximation to make the equation more usable. And as we know by our log rules, we can now rewrite entropy as the log of n factorial, big N factorial, which is our total number of students, minus the log of the denominator. And again, if we look at the denominator, we have log of a product. And when we take the natural log of a product, we can further use log rules. It just becomes the summation of all the logs that are multiplied. So then we have the summation of all the individual n's factorial. I think I'm gonna go to a new page. going to write a little bigger. Hopefully it'll still be easy to see. So I got natural log n factorial minus the summation of natural log of ni factorial. And that's our entropy equation, just reorganized with using log rules. And now we're going to use Stirling's approximation. So this ln of big N factorial becomes, as I said, big N times the natural log of big N minus big N. And then if we want to take a look at this part, becomes the sum of little ni times the natural log of ni minus ni. And now the summation, let's carry this minus sign here. So the summation of all the number of students in each group is obviously the same as the total number of students, so these terms will cancel. And now we're left with n times the natural log of n minus the summation of little n times the natural log of little n. Paper's getting a little turned. So now, if we want to kind of simplify this a little more, we can get probability in here, and the probability of a student being in any group is the number of students in said group over the total number of students, which we can set equal to the number of students in each group is equal to the probability of to be in that group times the total number of students. Now if we replace this in our summation term and carry everything down, we can get big N times the natural log of big N minus the summation of probability times big N, the natural log of probability times big N. Now we'll use log rules again. So we can split this summation into the sum of the probability times big N times the natural log of the probability, and then we add because the terms are multiplied. And this big N's a constant, so I could draw this out here. We'll do that. And that'll be multiplied into both terms. Or I'll just rewrite it. So summation and then plus big N again times the summation of probability times the natural log of big N. Now, if we take a look at this term here, we can see that we have the number of total students times the summation of the probability of each grade distribution times the natural log of the number of total students. And the summation of a probability is just going to equal 1 because it's the definition of probabilities that the total probability is going to be 1. So this term can actually simplify to n times the natural log big N. And just kind of an example to show that. So one of the examples I talked about was if the groups were split in two and there was 500 students in two different groups. And that could be kind of shown in this summation as like probability of 0.5 times the natural log of our total number of students, which is still going to be 1,000. And then since we have two groups, we'll have a second part of the summation with our other probability being 0.5 times the natural log of 1,000. So this this summation, if we combine like terms, becomes 1 times the natural log of 1,000, and 1,000 is just our specific example. This is really just big N. So basically this summation can become n times the natural log of big N. And since we're still subtracting this whole section of this equation, we have minus our summation of probability times big N, natural log of the probability, plus, now we showed that this can just be n times natural log of n. We still have this term out in front, which is our n times the natural log of n. This term minus the same thing will go away. So now we're just left with this term here, which is the negative summation of, I'll pull the constant out in front, negative times total number of students, the summation of the probability of the student being up. Looks like I was running off the page a little bit. Let's go to a new one. Alright, so as I was saying, if we simplify, it looks like it becomes the negative of the total number of students times the summation. Basically all that was left in this part. So negative total number of students times the summation of the probability of being in any individual group times the natural log of this probability. And then that's our new equation for entropy. And this is the equation that we're going to be maximizing in the next part of this video. We want to maximize entropy, which is also, we can think about as minimizing the positive value of this equation. So it should be the same thing.